Here's the basic setup for two-party communication complexity. We have two parties, two entities, two computers. Let's call them Alice and Bob. Alice gets to know one part of the input, let's call it X, and Bob gets to know the other part of the input, let's call it Y. And together they want to compute some function, f of X and Y. To do this, Alice and Bob might have to communicate with each other. For this, they follow a protocol, which they prearrange. So in the beginning, they agree on how their communication should work. They have some prearranged protocol for that specific function, and they follow this protocol when they talk to each other. This protocol determines who communicates next and what they send to the other person. So let's say the protocol says to Alice, if you have this or that value of X, then you send a 0 to Bob. And then Bob looks at the 0 he receives and the input Y that he knows of, and the protocol tells him that maybe he should respond with a 1 to Alice. And then Alice receives that 1 and can look at the 1 she received plus the input X she has and conclude that the protocol now tells her to send 2 zeros to Bob, and so on. So the communication goes back and forth in this way. And we follow this protocol, and in the end we have exchanged a certain number of bits between Alice and Bob. We can now measure how good this prearranged communication protocol is. And we measure the quality of the protocol by using a worst case input. So for the worst case of X and Y, how many bits do Alice and Bob exchange? So that is the cost of the protocol. And now we can define what the communication complexity of our problem is, of this function f that depends on X and Y. And the communication complexity of the function is the cost of the best possible protocol for that function. And we notate this as d of f. So that's the communication complexity of f. That's the best possible protocol that minimizes the number of bits that are exchanged between Alice and Bob in the worst case. Of course, the communication complexity of the function would depend on the sizes of the inputs. We can imagine that if X and Y are very big inputs, they contain many, many, many bits, then more communication might be necessary than if X and Y are both only a single bit or something like this. So in general, you should expect that this communication complexity of this function is a term that includes a variable that stands for the size of the inputs, so the length of X and Y. It's maybe best to use an example to illustrate this. Let's say we want to compute the OR function. Alice gets an input which consists of n bits, x1 to xn. And Bob gets an input which consists of n bits as well, y1 and yn. And what they want to compute together is the OR combination of all of those 2n many bits. So x1 or x2 or x3 and so on, or y1 or y2 or y3 and so on until yn. So basically they want to return yes and accept the input if any of their bits is 1, and they want to say no otherwise. There's a very simple protocol that would solve this problem and in some sense sort of circumvent the whole setup here. What we could do is we could simply say to Alice, send all your input, all your n bits to Bob, and then Bob knows everything he needs to know. He knows X and he knows Y now, and so Bob can just compute the function on his own. He will do so and compute the result of the function and then send the result back to Alice so that Alice knows the end result as well. How many bits of communication does this protocol need? Well, Alice sends all her bits to Bob. She has n bits to transmit, so she transmits n bits. And then Bob needs to communicate the result of his computation to Alice. But that is just a single bit. It's a 1 or a 0. And so that's just a single bit. So in total, they exchange n plus 1 bits. By the way, it's maybe debatable whether when we compute this function, Alice and Bob both need to know the result in the end, or whether it's enough if one of them doesn't know the result. But for our purposes, we will just assume that it's required that both parties, both Alice and Bob, have to know the result at the end of the computation. Although, as you can see, it really doesn't make much of a difference, because if only Bob knows the result, he can easily just communicate it to Alice. It will just increase the communication by a single bit. So it's not much of a difference, but let's just agree that both parties need to know the result. Okay, so this was a very simple protocol. Alice sends everything she knows to Bob. Bob does the entire computation and then just returns the result to Alice. We could have done it the other way around, of course. Bob could have sent all his input to Alice. Alice could have done the computation and then sent the result back to Bob. And this is a general idea that works for any function, really. So whatever function you have, we could simply say one party sends all their bits to the other party. That party then does all the computation and sends the result back. So in general, if we have a function that maps some space x times y onto z, then the communication complexity of that function cannot be larger than log of the size of x plus log of the size of z. And this is because this protocol shows that such a communication complexity is achievable. How many bits do we need to transmit from Alice to Bob? Well, she just needs to indicate which input she got. And there are size x many different inputs. And so we only need to transmit log size of x many bits to identify a specific input. And then for the results, if the result space is z, then we need to communicate back which specific result we got. And this requires log size of z many bits. You will notice that I did not assume here that this function is a decision function. So if it's a decision function, the output could only be 0 or 1. So this set z would only contain 0 or 1. So it would be a set of size 2. But in general, this function could be something different. It doesn't have to be a decision function. So I kept it more general. For the OR function specifically, the question is, can we do better than this rather naive approach? And it turns out you can. And I think you can come up with this yourself probably, but let me just tell you how it works. Alice can simply compute the OR of her input bits. So she would compute x1 or x2 or x3 and so on. And then she would send that result to Bob. Now, this is only a single bit that she now sends to Bob. And then Bob computes the OR of all his bits and the result he got from Alice. And then he sends that result back to Alice. So clearly this works. Basically, Alice just checks, do I have a single 1? If yes, I will tell Bob, yeah, I have a 1. Otherwise, I will tell Bob, no, I don't have a 1. And then Bob checks, do I have a single 1? And if yes, I will tell Alice I have a 1. If no, I will check whether Alice had 1. And if she did, I will also tell her, yes, the result is 1. So what is the overall communication here? Alice transmits a single bit to Bob, and Bob transmits a single bit to Alice. That's it. So the cost of this protocol is only 2 bits. And in fact, in this particular case, the cost of the protocol is independent of the input size. It doesn't matter how many bits Alice and Bob started with. You will notice that this is a drastic improvement of what we had before. Our naive protocol used n+1 bits, and now we only need 2. So sometimes it really pays off to be a bit more clever. Of course, this was a very simple example, and you might say, who will care about computing an OR function and so on. But we can have more interesting examples where it's also not so easy to come up with the right answers. So that's what we're going to be doing next.